Okay, so we're starting chapter 3, and chapter 3 is going to deal with exponential functions and logarithmic functions. And we're going to start off with talking about exponential functions. Now, the definition of the exponential function says the exponential function f with base b is defined by f of x equals b raised to the x power or y equals b to the x power, where b is a positive constant other than 1 and x is any real number. Now these are very, very important because all of the problems that we're going to deal with, all of the exponential rules that we're going to learn, they only are going to apply if you have a non-negative and non-equal to 1 base. So b must be greater than 0, which means it can't be 0 and it can't be negative, and b cannot equal 1. If b is equal to 1, it doesn't matter what power you raise it to, 1 to the 10 millionth power is just going to be 1. So it's kind of one of those one-offs by itself. So that's what we're dealing with here now. And 0, of course, to any power is going to be 0. And if we deal with a negative, well, remember, if you got a negative raised to an even power, it's going to be odd. Think about negative 1 squared. But if you think about negative 1 to the third power, it's negative. So the problem with dealing with b values that are negative, if we have negative 1 squared, that's a positive number. But if we have negative 1 cubed, then that's a negative number. But the thing is, where between 2 and 3, remember these are our variables, where between 2 and 3 are we going to be able to raise it to a power that's going to make it 0? See, that's the thing. It's not going to be a continuous function. So we're going to run into problems there. That's why the exponential stuff doesn't work for values, for bases that are negative. And if the base is 1, well, it kind of takes care of itself. All right, so here are some examples of exponential functions. F of x equals 2 to the x, the base is 2. 10 to the x, the base is 10. 3 to the x plus 1, the base is 3. The power is x plus 1. Here you got 1/2 raised to the x minus 1 power. The base is 1/2. Each of these functions has a constant base and a variable exponent. Now, in the other way, here are some examples of things that we've dealt with that are not exponential functions. Here we got x squared. The variable is the base, not the exponent. So in that case, that's not going to be an exponential expression. Now it's still a function, and we've dealt with that. It's a parabola, but it's not going to be an exponential function. Exponential functions have to fit the definition we've set for it. With the capital G of x here, we have 1 to the x. Well, the base can't be equal to 1, therefore this is not classified as an exponential function. Does it fit almost all the definition? Yeah. The base is a constant and the power is a variable. The only problem is we've got limitations on those bases, and this violates one of the limitations. Same thing here with capital H. Capital H of x is negative 1 in parentheses to the x power, and that's a situation where the base does not fit within our limitations of the base, therefore this is not going to be an exponential function. The base of an exponential function must be positive. And then here at the last, we've got x raised to the x power. The variable is both the base and the exponent, so that's not an exponential function as well. This is something else. All right, now the exponential function f of x equals 42.2 times 1.56 to the x, and it models the average amount spent in dollars at a shopping mall after X hours. What is the average amount spent to the nearest dollar after 4 hours? All right, so at that point, X is the number of hours, So if all we're doing, we're going to find f of 4, which means we're just going to plug in 4 everywhere we got an x. So we have 42.2 times 1.56 raised to the 4th power. All right, and then we're going to use a calculator, and we're going to get $249, and we get 0.925, so I'm going to round that up to 0.93. So according to this exponential function, if you spend 4 hours at the mall, you're going to end up spending $249, almost $250. Now, what would you have if you had, let's say, 3 hours? So you guys try this, grab you a calculator, some way, shape, form, or fashion, and try this. You're going to want to put it in. Remember to multiply your 42.2 after you've raised to the power, if you've got to do it in that order. Be careful and don't multiply 42.2 times 1.56 and then raise that to the x power. So you guys try this, and I'm going to pause the video, try it, and when you get ready, come back and check your answer. I'll show you the answer in 3, 2, 1. Alright, so if you put your 3 into your equation here and calculate it, you're getting 160.21, and that's going to be the approximate amount, modeled or expected by this function for you to have spent if you spend 3 hours at the mall. Alright, so let's graph an exponential function here. And it's really, really easy. We're just going to do a T-chart just to kind of give you an idea of what they look like. And we're going to start with 3, 2, 1, 0, negative 1, negative 2, oh, it's a big negative, and negative 3. So there's my x value, and I'm going to find my y value, or my f of x value. So if I raise 2 to the 3rd power, I'm going to get 8. If I raise 2 to the 2nd power, I'm going to get 4. 2 to the 1st power, I'm going to get 2. 2 to the 0 power, remember anything raised to the 0 power is 1. 2 to the negative 1, well remember it's just this thing right here, and then flip to the bottom. So it's going to be 1/2. Same thing with the negative 2, it's this thing right here, but flip to the bottom. So it's 1/4. And negative 3, it's the same thing as 1 over 2 to the 3rd, so it's going to be 1/8. So now I can plot these points, 3, 8, 2, 4, 1, 2, 0, 1, negative 1, 1/2, negative 2, 1/4, negative 3, 1/8, and you can kind of see what's happening here. As you get further and further on, it starts growing and growing and growing. Now, you may have heard about things that grow exponentially. This is where that comes from. Look at how fast this thing's growing. This thing's growing fast, and not only is it growing fast, but it's going to grow faster. If you look at the slope here versus the slope here versus the slope here, it's getting steeper. From 0 to 1, it only went up 1 point. But yet from 1 to 2, it went up 2. And from 2 to 3, it went up 4. And it's going to multiply by that. It's going to increase by a greater rate every single time. So it's going to grow at a faster rate the further it goes. That's what it means by graphing an exponential function. Now, you're going to need to be able to graph this not only are you going to be able to need to graph this, but you're going to need to be able to graph it without any. But not only that, we're going to actually get into the logarithms later in the chapter. And logarithms are nothing more than the inverse of the exponential function. So you're going to have to know what these points are, and you're going to have to flip them around to be able to graph an logarithmic function. So knowing how to graph these are really easy. But it's really easy. 2 to the third power, 2 to the second power. Just get you some values of x that are small, and you're going to get this shape right here. Regardless of what the base is, it'll give you the correct answer if you just plug it in and figure it out. All right, you guys try 3 to the x, and I'm going to pause the video again. I want you guys to try to sketch this, and then we'll come, I'll show you what the answer is in 3, 2. All right, so here's the graph. And one thing you'll notice is that the larger the base is, the faster it's going to grow. Here we go from 0 to 1 and it goes up 2 units. And you go from 3 to, or from 1 to 2, and it goes all the way up 6 units. And what you're doing is you're just multiplying by 3 again each time you add an x. So we've got 3, and then times 3 gives you 9, and then times 3, the next one will give you 27, etc., etc., etc. And how much it's changing, notice we've got 2 here, and we've got 6 here, so it's changing at a faster rate even than the 2 to the x we had before. So the larger the base is, the faster it's going to end up growing. And in the same way, over here on this side, and we didn't really talk about it on the 2 to the x, but as you go over here, the larger this base is, what do we notice? The faster we're actually going down, because here we've got 1/3, here we've got 1/9, here we have 1/27, and I couldn't even estimate how far down that would have been. It would have been really close, lower than what I've got right here. It would have been down really low, and then essentially my red line becomes the same thing as the x value, or as the x-axis there. So it's going to grow really fast in this direction, and it's going to get really close to 0 in this direction really fast the larger this number goes. And the thing is, you're never going to equal, remember, there's no way, we have 3 to the x, when is that going to equal 0? Well, it's never going to equal 0. And it's never going to be negative. So it's going to get closer and closer and closer to 0 when we get over on the negative side, because we've got, like we said, 1/3, 1/9, 1/27. Each time we're multiplying the denominator by 3 again. So 1 over 81, 1 over 243, etc., etc., etc. So that's how small this is getting. The larger in the negative direction we go, the smaller this fraction gets, so it gets closer to 0. But it's never, ever, ever, ever going to be equal to 0. So what we have here is a horizontal asymptote at 0. It behaves exactly like the horizontal asymptotes we had with our rational expressions, so we can treat it that way. Now, it's a horizontal asymptote only on this side because we're dealing with negative numbers. And negative exponents here are going to make that thing have a 3 to the x on the bottom. So that's why that works. So it's only on this side we've got a horizontal asymptote, and it's going to be 0. So we can use that to shift it up and down as we need to. All right, I want you guys to try this one. It's real simple. It's 1/2 to the x power. And remember, you're just multiplying it times itself that many times. So I'm going to pause it. I'm going to work the problem out, and then I'm going to show it to you. And I'll show it. I want you to pause it and try to do this as well. You need to work with fractions because you will see fractions over and over and over again. So try the problem, graph it, pause the video, give it a try, and then come back and check, and I'll show you the answer in 3, 2, 1. All right, so here's the graph for this one. Now, there's a couple of tricks here that you could use to actually get this a little easier to deal with, if you don't like the 1/2, the fractions, well, remember, you can always flip this over and change the sign of the exponent. 1/2 to the x power is the same thing as 2 to the negative x power. Because remember, a negative exponent does what? Just flips the thing over. So in the same way, if we add a negative exponent, we can flip the fraction over inside. Either way, you're going to get the same thing. If we take 1/2 and multiply it times itself, 1/2 times 1/2 times 1/2, we're going to get 1/8. Same thing with the 2, the 1, and remember, anything to the 0 power is 1. Now, with the negative 1 here, the way you could do it if you didn't change it over into this, you've got 1/2 to the negative 1 power. Well, once again, negative 1, negative powers just mean you flip the fraction over. Same thing with 1/2 to the negative 2. Flip it over and square it. If you flip it over, you're going to have 2 over 1 to the 2nd power. And then, of course, that's going to give you the 4. So there's lots of ways to deal with this, but just get comfortable with the fractions, because here's a breakthrough here. You're going to see fractions. They are not going away. All right, now characteristics of exponential functions of the form f of x equals b to the x. These are some characteristics, some very important properties that you need to remember. The domain of f of x equals b to the x power consists of all real numbers, negative infinity to infinity. That's the domain, the x values that you can have. The range of the base formula f of x equals b to the x consists of all positive real numbers from 0 to infinity. Remember, the base exponential will never be negative, and it's going to approach 0 but never get there. Hence the parentheses here. We have parentheses and we don't include 0 because we're approaching 0, we're not actually getting there. All right, the graphs of all exponential functions of the form f of x equals bx pass through the point 0, 1, because f of 0 equals b of 0, and anything to the 0 power equals 1, as long as, of course, as b doesn't equal 0. The y-intercept is 1. There is no x-intercept because, once again, b to the x is going to approach 0 but never actually equal it. Now, if b is greater than 1, f of x equals b to the x has a graph that goes up to the right and is an increasing function. It's always going up. The greater the value of b, the steeper the increase. Now, if b is between 0 and 1, f of x has a graph that goes down to the right and is a decreasing function. It's always decreasing, and the smaller the value of b, the steeper the decrease. F of x equals b to the x is 1 to 1. Remember, that means that it is a function and its inverse is a function. And the graph of f of x equals b to the x approaches but does not touch the x-axis. The x-axis, or y equals 0, is a horizontal asymptote. Now, guys, be real careful and understand this. These are properties of the base graph. The base graph of f of x equals b raised to the x power. If you start adding and subtracting things to this, that's a transformation. We're talking only about the base graph here. You could easily say -1, and you're going to drop this whole thing down, and of course it is going to hit the x-axis. So understand, these characteristics and properties only apply to the base graph. Don't magically think in your head, oh, every exponential function is always going to do these things, because it's not, especially not if you subtract or add or shift in any way. All right, now I'm not going to go through all these because you guys are grown-ups, and if you look down at the bottom there, this table is on page 392 of your book. Do not copy it down. All these transformations, vertical translation, horizontal translation, reflection, all this stuff, guys, it's the same thing we've been talking about since chapter 1 with those base graphs from the very beginning. If you know how to do those translations, you're going to know how to do these translations. get that key point of 0, 1, and do any translation you need to it, and the shape's going to essentially stay the same. Just remember about the reflections. That's going to change the shape or the direction it's going to go, but the overall shape's going to be the same. All right, so if we were to graph f of x equals 3 to the x, I'll do that real quick. We got 0, 1, we got 1, 3, we got 2, 9, we got negative 1, 1/3, negative 2, 1/9, and you get the idea there. And look. Oh, that was classic. All right, so you get the idea. I'm not going to spend a bunch of time getting this right, exactly right, which I'm never going to do. So if we were to have g of x, this is f of x, and let's say we're going to graph g of x, and I'll do it in purple, and we have 3 to the x plus 1, well, is that inside the function or after the function? Well, that's inside the function because it's inside the power. So what's going to happen? We're going to take this thing and we're going to shift it 1 unit to the left, because inside the function we go the opposite of the way it's supposed to go. This is my key point, but here's the thing that's awesome. You can take every one of these points and move them over to the left 1, and there's your graph. So this one would move over to about right here, this one would move over to about right here. So you're going to have a graph that's going to look like that. So there is your graph. Every single one of the points just shifts 1 unit to the left. So all those transformations that we've talked about in the past are exactly the same way in their application to what we've got here with the exponential functions. So same thing here. We get 2 to the x. Use the graph of 2 to the x. So I'm going to go ahead and graph the 2 to the x in green again. So 2 to the x, remember 0, 1. That's that 1 point that's always there. Go over 1. 2 to the first is 2. 2 squared is 4. 2 to the third is 8. 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4 and 1/8. So there's the rough idea of what this graph's going to look like. And then we want to graph 2 to the x minus 3. And I'm going to do that in blue this time. So what happens to every single, remember the original point, I want you to kind of think through this and understand why this is true. Let me change colors here for just a second. Right there, g of x, that's the exact same point. So all the y values are exactly the same for g of x. Now what happens if I throw this in here? Well, every single y value is just going to be 3 units less. So that means this point right here is going to go down 1, 2, 3. This point right down here, 1, 2, 3. This point, 1, 2, 3. Every single one of them is going to go down 1, 2, 3. 1, 2, 3. 1, 2, 3. And you get the idea. Now, here's the thing that you need to remember. If you're just sketching this, you don't actually need these points. You will need this point, which is your base point, but also don't forget this horizontal asymptote that's running through here. If you take that horizontal asymptote and drop it down 1, 2, 3, then it's now going to be right here, and you know that's what you're approaching as you go off to the left. So that's where that minus 3 comes in. right, now we have, and you've seen this, e to the x. You've seen it on calculators and all kinds of things like that. Well, here's the thing. E is the natural base. What that means is it's something that occurs over and over and over naturally in nature, in calculations about nature. But e is the natural number, and it's approximately 2.718281827. And it continues on forever. It does not repeat, very much like pi. So when you see e to the x, it's just this number raised to an exponential, raised to a power. So if you see e squared, it's just 2.718281827 squared. It's just the number. But e is a base. That's one of the reasons why you're not typically ever going to see e used as a variable. Now, some formulas for compound interest. After t years, the balance A in an account with principal P and R in decimal form is given by the following formulas. For n compoundings per year, A equals P times 1 plus R over n to the nt. Now, make sure you know what everything is here. P is the principal, that's the amount you put in at the beginning. R is the rate in decimal form, so if it's 6%, you're going to use 0.06. And n is the number of times compounded in a year. So that's what n is, number of times compounded in a year. And t is the number of years. Now, with continuous compounding, we have A equals P e to the RT. Once again, R is the same thing. It's the rate in decimal form, and T is the number of years. Now, you do need to know how to use these formulas. We'll do some of those in class, and we'll talk about them, but make sure you jot these equations down. You will use them. Most of the time they'll be given to you, but you do need to remember some of what they are and what they actually find.